See?
Yeah. Oh, yeah.
Well, I mean, you could think of songs, but
The classical tenants, yeah. I mean, our repertoire is sort of fairly fixed by what we define. We will not play move pen.
good. Thank God.
Yeah.
If you want. Yeah? I'm not sure. Is there someone sitting here? No. Just don't knock over the thing.
Hey Jimmy, do you have my cable?
Oh. I'm sorry, I was going to give it back to you, but Bob said he'd give it back to you, and I gave it to Bob.
Okay.
I'm sorry.
I'll give you up.
Oh. This cable.
Being slow.
It's okay.
Who knows Greek?
The slow is synonym for stealing.
Who makes the noise Greek? Jamie, you must know Greek.
Fancy coming in. Wow, huge screen.
Yeah.
It's quite exciting.
I just
It's like
got
the sharpest screen I've ever seen on the camera.
The thing is, you take one picture, but it's 9 pictures.
Oh, that's a lot. Okay, we'll figure it out.
When you know where to look.
I'm really surprised if I could take that video and this could.
I don't know.
Does that do HD? This will do HD, 720p maybe?
Yeah, of course it does, but it's no fun asking
old,
to read
this
his
thing.
own shirt. But you should say, like, I think
Yeah, it's quite possible. But you put it to the text. You have candles?
Candle?
You just put it in the candle mode.
Yeah, I don't know what candle that is.
Night mode.
What's that idea?
Romantic.
Yeah, because in pitch dark night it's somehow ridiculous to expect the thing to
The
look
14th?
Does it reduce the number of pixels?
I think how pair words together.
I doubt it. Complicated.
Something came up saying it's 2.5 million pixels.
Yeah.
Oh, that would be really clever. It's built in.
Because like
Makes sense.
two convex zones,
Some
some
cameras
XI,
actually did that.
you find
I'll look for how to do it, and then I think actually
assume there exists an XI style that is
Also around the
less than or equal
so it's got two physical rings.
strictly less than the YIs.
Ah, good face detection.
So you can do that without loss of generality, right? Because if they're all equal, then you're okay. And yeah. No, I'm taking these sums, right? So I have two convex sums, right? And so, right? And so I'm assuming that there's some xi that's not equal to yi. Because if they're all equal, then none, right? So assume there's one that's strictly less than. These are just real. So assume there exists an this is a real SIs. Yeah. I'm just taking a convex sum of the operators defined by these linearly.
I thought the XIs were added up to 1 where you could make your own one.
They are.
I thought the SIs were unitaries.
They are.
And I thought this was a matrix.
Yes.
Okay, so what's real?
I mean, these are convex sums.
Right, okay. So assume some XI is less than or equal to some YI.
Strictly less than.
Strictly less than.
Right.
If they're not equal, it's
Right. Right. And so you want to bring that xi. Sorry, you want to bring that yi. Yeah. So you want to have. So you now want to rewrite this as. Right. And then we'll have one of these. We'll have a negative. It'll be a negative. Like YI is only negative. So the left-hand side is not going to be completely positive. And then it's SI formulated. Yeah, that's yeah. And the right-hand side is
So it's still complex. So,
right. Well, it's still a positive, so it's not
or not complex.
right.
But one is I would say
They should just accept the idea.
you can remove lines it can be a complex sum and then it's a scalar function.
You don't have to do that. You just have it's yeah you have this CP math if and only all of the constants are greater than 0. Right, so convex sum is yeah. And this should just
Good to know. So it might actually
It sounds like it should.
right.
You can use a core to make
I really want to see it.
What are you doing, Jimmy?
Is that on video? I need that now. Actually, wait, no. Yeah, get a video of me here right now. I need it. You guys remember I'm right here. Yeah, I need witnesses. Thanks, well, it could be nice to get manual focus.
Yeah, I thought there would be that ring function. Like,
Oh, it depends on the mode you're in. You have to be in PM or... You did it manually. You can definitely do it in manual. You can probably do it in PM as well.
So, couple of quick announcements. I tried to restart wireless. I hope it'll now work. But she was on repeater too, so she claims she was getting wireless downstairs in that room. At some point, Laurie, if you want to go and look at the wireless router, I'll pull the plug out and shove it back in, which is the most advanced thing I know how to do. Power cycle. Power cycle.
I think in the meantime, people can wire it to the internet for cars and stuff.
Yeah, that's not the best. It's very slow. Anyway, okay. So today's the last day. I'd like to, first of all, remind you to pay your bills before you go. So the office is open. Celia's office. You may have to go around the side of the track. But she takes credit cards. So you can settle up before you go and give her your keys as you're leaving, or give me the keys. And
She's open tomorrow as well.
yes. Some people are starting to leave today. Second thing is, so tomorrow is the last breakfast. There won't be dinner here tonight. And I'd like to give a small gift to the cooks for all the cooking. So what I will collect, entirely voluntary of course, but those of you who are willing to contribute, my suggested amounts are 5 for students, 5 Barbados, and 10 Barbados for people who actually have jobs. Okay, so Bob is the chair of the session.
All right. My friend was hoping that I was going to still be drunk this morning, so I have actually made it up the chair. So first speaker is Mehrnoosh.
Thank you for that dynamic introduction.
Okay, so once upon a time there were 4 children living in a countryside house close to Oxford, because it was just in the Second World War, and because of the war for some reason you have to go and live in the countryside. And it was summer and it was hot, so they decided to take a tour in this big countryside house. And then one of them finds a wardrobe, and they decides to enter the wardrobe.
It was raining.
Was it raining?
Yeah.
It was summer anyway. So as she, and her name was Lucy, so as she enters the wardrobe, she starts to go further and further, deep into the wardrobe, pushing away the fur coat and all the other things. And suddenly she realizes that the fur coats have become branches of a tree, and she finds herself outside in a winter in some land full of snow covered in white stuff, and there was a lamppost, and she's totally confused. And she looks around and she sees a strange person with ears of a goat and the tail of a cat.
Her name is Lucy, you said.
The girl is called Lucy.
Imagine with a song. No.
With diamonds.
Recognize
Diamonds.
This song.
the sky. LSD, you know.
Anyway, so this strange person was carrying a brown bag full of Christmas presents. So, and then Lucy says, "Good evening. I don't want to be inquisitive, but should I be right in thinking..." So this guy says to Lucy, "Good evening, I don't want to be inquisitive, but should I be right in thinking that you are a daughter of Eve?" Lucy says, "My name is Lucy," looking a little bit puzzled. And he said, "But you are a girl, right? A human?" Lucy says, "Sure, I think I'm a girl and a human. May I ask, oh, Lucy, daughter of Eve, how you come into Narnia?" "Narnia? What's that?" "This is the land of Narnia, all that lies between the lamppost and the eastern sea. And did you come from the wild woods of the west?" "No, I got in through the wardrobe. The spare room," says Lucy. Okay, so it's very weird, but I bet all of you understood what I said. We all understand, but it's so weird. How are we able to assign meaning to this kind of thing? So the title of the talk is Chronicles of Narnia. So there is two theories of meaning in computational linguistics. One says we understand things, for example this text, because we translate them to first-order logic formulae and logically universal language. That's why we understand them. I don't think that's the case here.
I have a complete translation for you. Meanwhile, I translated everything you said.
Can you model check and say if it's true or false? You should do it. And then there's another theory of meaning which I'm going to talk about today, and that's called the vector space model of meaning. So it says we understand the words, weird words like Narnia. I've never heard of Narnia. Witch, white witch, and Aston. These are the words that appear a lot in the book. We understand them because of the context in which they appear. So the word Narnia, if you look at this book, for example, appears a lot close to island. So we know that Narnia is an island. And it also appears a lot close to the word lamppost. So we know that it's some sort of a fictionary place. The word witch appears close to winter, to terrible, to all the bad adjectives. Terrible, horrible, cruel, dangerous, etc. And the word Aslan, the lion, appears close to spring, to all the good things. Spring, king, lord, lion, etc. So you see what I'm trying to set up. So if you run into such a text, you sort of look at the words that you're familiar with and try to decode the words that you do not know based on how the proximity of these words to the other words that you know, yeah? So if I just now look at this table that I've made, I can say that the witch, the character witch that appears in this book, has some bad connotation because it appears close to these bad things, winter, coldness, terrible and horrible. And the Aslan guy has a good connotation. It appears close to spring and king and lion, etc. Yeah? So these people said, why not 5. And then we're going to count the word that we do not know its meaning, how many times it has appeared in this window of five words close to these other guys which are the basis of our vector space. Yeah?
And this idea of closest a parameter on the distance between the words? Like 2 words away or what do you mean?
Yeah. So actually I have some examples. For example, when I was telling this to Emma, she said, I've never seen the word island there, right?
Yeah,
Island. Okay, here's a sentence. So this is towards the end of the story, when they all go back and become big, and so I say, said King Edmund, and I have such desire to find the signification of these things, so all these wardrobe and these stories, that I would not, I will return back for the richest jewel in Narnia and all the islands. And you see a lot of islands close to Narnia towards the end of the book. And here's an example from The Witch and Terrible. The White Witch is a perfectly terrible person, said the faun, the strange-looking guy with ears of the goat. She calls herself the Queen of Narnia. She can turn people into stone and do all kinds of horrible things. She, the witch, has made a magic so that it's always winter in Narnia. Always winter and never Christmas. So you see these words appear close to winter, a lot close to winter. Okay.
Mehrnoosh, I have a quick question that I don't want a technical answer to right now, but like in some of these groups you've already grouped together several words like dangerous, cruel, horrible, and terrible. So is there a sense in which you determine that they're related to each other? And
No, I was just lazy. I didn't want to write all the words in line.
Okay, just all that.
So you're trying, I'm trying to sort of convince you that there is a bad connotation to reach. So some people with bad attitude.
Okay, but if you lays them out, then it might look something like 72222 or something like that, right? And then maybe it's not as clear, the relation between.
I doubt it. It actually does appear close to all these adjectives.
Okay.
If this is our only model of meaning, if this is how we extract all the information we can from the text, how do we know that Narnia isn't a lamppost? How do we know that Narnia is an island?
Why would you think that something here is something there?
Well, as you were describing it, you said, so we know Narnia is an island because it is close to one. We know Narnia has a lamppost in it. It's close to, but aren't we using more to make that interpretation?
Narnia has properties like this, like being an island, being close to a lamppost. The Queen has properties like winter light, being terrible.
Yeah, but maybe it's right. I mean, say it is an island and it's close to a lamppost. So why do you say it is a lamppost?
I don't know where to get this verb. So we just want to say that this word has appeared close to these other words. So if I want to put it in simple terms, so I want to say this word has properties like that. But so to say what is a property? Being an island.
But after reading the book, we are aware perhaps that Narnia is an island. We are aware that it has a lamppost in it. So how do we get? Okay, suppose it were an island. How do we get that extra?
All you can say is that Narnia has this sort of property. Properties close to an island. Being an island. Properties of being close to a land. So when you go home, you remember that Narnia, there was some element of being close to a lamppost for Narnia and not for Aslan. Yeah.
Can you read the last sentence about the witch again? There was she, not the witch, in the actual sentence in the text?
So do you want to talk about this reference?
Yeah.
So there are ways to resolve references.
And then you put that in here in the row with which after resolving it?
So when you parse the sentence, you sort of when you see pronouns at some places. For some which are not ambiguous and are easy, you know, you can replace the pronoun with the verb, the noun that it refers to.
So that's a pre-processing in advance of doing this counting of it.
Taking into account relations.
Relation.
You read the sentence says something like always winter and never Christmas.
Actually, from Christmas appears only in this sentence.
Okay. But potentially could show up very often. Always associated with something.
The Father Christmas appears quite a lot,
So, do you always have to have a basis of words that you know in order to try to assign meaning to other words? Is that?
So maybe I should, so I set up this for this purpose, but yes, so not necessarily. This is a very good example, but you can do it for all words. So you can even put island here. So you can look for the bases using other bases. So you can put lamppost here and winter here. So these other weird words. And then it's maybe a good idea not to think of things very literally and in their own here, but in relation to other words. So once you have set up your big vector space, you get vectors for all these words, and then you can compare the synonymity by the distance of these vectors. So that's one of the big applications that came out of this setting, make this a winner. So you can now automatically decide which pairs of words are synonymous and which are not. And that's one thing that comes out. Yeah?
How do you deal with negations? I mean, there could be lots of sentences which say Narnia is not an island, so they would still be very close, but the statement is exactly the opposite.
Yeah. But we're not talking about statements here, of course.
So you want to extract the meaning.
Yeah, but that's a problem, yes. So, yeah, okay, so we do, at the beginning we said there is a logical model of meaning that translates sentences to first order logic formulae, and that's a bad model, but we dumped it, but let's keep one good idea from it, and that not all the words are at the same level. Some are predicates, relations, and some are atoms to which these predicates apply. So for example, here I've got only nouns, Narnia, witch, and Aslan. How about if I'm interested to compute the meaning of a verb? For example, the verb order. We've got a lot of sentences that this witch guy orders people, orders them around. So the witch ordered the lion to lie down. And at some point in the story, he orders Turkish delights to fool the human being. How about the verb? So we argue it's not a good thing to build the vector of the verb like this, like the noun. But you want to go a bit higher order and think of the verb as a relation that connects two nouns and build a matrix, not just a vector, not just like a row matrix, one-dimensional, but for example, for the case of transitive verb, because it connects two nouns, a subject and object, you want to build a two-dimensional matrix for it to encode the fact that this is a relation connecting these two words. So I've set up this matrix, and we want to, for example, think about the weight. So here it's easy, you just count if Narnia has appeared in your 5-word window close to island. But how about if I want to talk about the word order in the cell C35 of this matrix? In general, the cell CIL. How do I assign a number there? So we say, okay, this is not just the verb connecting an object and a subject, which is normally, well, that's what normally is done in logic. You say two things are related by relation, thus the value will be 0 or 1. But you want to actually put some numbers in there. So let's interpret it as the extent according to which the transitive verb connects its subject to its object. And what does that mean? So we've been experimenting with this a little bit. So you look into your corpus, in your text, and see how many times the word order has appeared in sentences. Suppose twice. In the sentences, the witch ordered the lion to lie down, and the witch ordered Turkish delight for Edmund. And then you're going to look at the subject of the verb. So we're interested in the value of the cell CIL. Look at the subject the cell C35, and I look at that sentence, the which, so I want to see how many times the which has occurred close to N3, which is winter. And I know how many. 7 times. So I put my 7 down. Times, how many times the object of the verb has occurred close to NL. So in this case, how many times the lion has occurred close to basis 5 spring. So taking the lion to be the same as the Lord and the King, 8 times. Winter and spring, sorry, 7 times. So multiply the two, 7 times 7, and repeat this procedure for all the sentences. So now we did it for the which ordered the lion. So repeat it for the which ordered Turkish delights, for example. And then sum all of them together. Yeah, and that will give you the value of the cell CIL. Yeah? Is that clear?
Do you have a way to normalize the numbers to the size of your corpus
Yes, very
and
good,
stuff
yes,
like that?
yes. So normally you don't actually count. There's a measure called TF-IDF, term frequency, inverse document frequency. So you count how many times your word appears close to the basis, divided by how many times all the other words appear close to the basis. So this will get rid of the anomalies. Like if one word appears mistakenly close to some other word, it will get eliminated. There are all different ways of normalizing based on the application that we want to do later on. Okay, so I've set up some numbers here. So for C35, based on these two sentences, so you get 7 times 7 plus 7 times a very small number. Because Turkish delight hasn't appeared close to spring very much. It's something that appeared close to winter because it's a green, the which you gave Turkish delight. So this is new, this is what we did. And now that we have a matrix for the verb and vectors for sentences, we would like to approach a challenge open for 50 years in computational linguistics, how to build meaning for sentences, vectors for sentences like we have vectors for words, based on the matrix that we have for the verb and the vectors, the one-dimensional matrices that we have for the subject and object. For example, consider transitive sentences like the which ordered Aslan, the which ordered Turkish delights. And I claim that the meaning of a transitive sentence in general, so you have your subject, you have your transitive verb, and you have your object. We want to build a vector for it, like we have vectors for the meaning of word. And I claim that this guy is in fact equal to, look at the two-dimensional matrix of your transitive verb and rebuild it this way. Take it pointwise multiplication with the tensor product of the vector of the subject and the vector of the object. And these two guys we know from here. Yeah? So now I can build meaning for the which ordered Aslan by saying, look at the two-dimensional matrix of the verb order, take its pointwise multiplication with the vector of the which, tensor product, vector of Aslan. And you can really, if you're quick, you can build the 6 by 6 matrix for the meaning of this sentence. Yeah? For example, at some point there will be 7 times 7 plus 8 times 7, etc. Yeah, so we have a matrix for the meaning of the sentence, compositionally built from the meaning of the verb and the meaning of the subject and the object. So that's a breakthrough. People were not able to do this for 50 years.
Can I ask something about that example? Because the verb order in those two cases has slightly different meanings. So the first one actually makes less sense than the second. So
that's on purpose, yeah.
Okay, good.
Yes.
So tensor product symmetric?
Tensor no between the two vectors. Well, it's pairing, so yeah, to some extent.
It should should play role. Who orders?
I know, yes, and this, at the end it will become clear why you cannot just switch these things around.
Okay.
So I'm going from bottom up in our approach. So you get to this from some higher order categorical prescription. It doesn't allow you to do things the other way. Yeah, you don't need to think about it. Because this guy is also commutative in the convolution. So now we have a big matrix for the vector of the sentence, but what does it mean really? One application of this setting, as I was explaining, is to sentence synonymity. So we claim that we can use this method to see how synonymous sentences like the which ordered Aslan and the which ordered Turkish delights are. So we build our huge vector space, we have vectors for these guys, and we just measure the cosine of the angle between them. There are so many different bases. Here is the vector of S1, and here is the vector of S2. How synonymous do you guys think these two sentences are? Like you were saying, the meaning of the verb is not synonymous. It has slightly different meaning in these two sentences. So how synonymous do you think the two sentences are?
And it's not just that, because the first one you want the order as like to do something, to lie down.
Yeah, yes, yeah. So you have put dot for it, to require. So the program, so let's just put one more sentence. The witch lived in Narnia. And let our method calculate the angle between the which ordered Aslan to lie down and the which ordered Turkish delights for Edmund. How synonymous they are, so you get a number here. And compare this to the synonymity measure of the for the pair of sentences the which ordered Aslan and the which lived in Narnia. So how synonymous do you think these two sentences are? S1 and S3. Again, in their own, it doesn't really make sense, but if you compare the synonymity measure of S1 and S2 to the synonymity measure of S1 and S3, you will see that, that this method says that these two sentences are slightly more synonymous than these two sentences. So the which ordered Aslan is closer to the which ordered Turkish delights than the which ordered Aslan to the which lives in Narnia. Slightly. Not so much. So here you get something like 0.7, and here you get something like 0.6. Not too much difference. But the merit of the method comes out if you compare the meaning of these two sentences to the meaning of the which ordered Aslan to lie down and Lucy was sad, or the sky is blue. Then these two sentences are way more similar than these two sentences. And now we can say something meaningful about it. Are you all lost? No.
That's actually related to what he just asked. The two ordered should be kind of considered different words, because one has got two objects and one has got one object.
Yeah.
And like, can you take that into account somehow?
Yes, so this method, I was going to explain later, is used for disambiguating exactly this kind of different meanings of sentences. Yeah? So if you replace here the which ordered the lion to lie down with the which asked the lion to lie down, and the which asked Turkish delights for Edmund, so the two sentences have to be close in their meaning, so ask is close. But if you here say the which bought Turkish delights for Edmund, the which bought the lion to lie down, this is not going to make sense, and these two sentences will be far apart. So now you can decide that order might have two meanings, bought and ask, being asked for something. Yeah, then you can use these cosines to measure the synonymity of those other sentences, and then compare it with order being put in the wrong context, etc. Yeah?
Does it work always well, or you have some cases in which it tells you that two sentences are closer to other two sentences where like this?
Okay, yeah. So here, this is do this word. It's actually very hard to decide what is the correct answer. So you have a theory, and you can measure synonymity, but is it correct, the synonymity that the program gives you? How can you decide? Yeah.
I think I'm just going to repeat the question that they asked. The thing is that it's not only whether they have the same meaning, but I think they have a different grammatical. So one of them.
Yeah, one is
one
dichotomy,
object,
one is transitive.
Yeah, one of them has two objects.
Yes.
When you give meaning to both the two objects, you basically count those objects.
But order can also have a transitive meaning. So you say the which order sleep. That's transitive.
Yeah.
The which order shut up.
Wouldn't that?
No more questions.
She ordered.
Why is it that you try to present some new results? Everybody sees the negative point all the time.
What is the? I'm not sure where the angle of the vectors comes from. Like, I get that you're multiplying different quantities and we get a number, but how do we get them at different angles from each other?
Oh, so the meaning of the sentence is a big matrix.
Yeah.
Which you can represent as a vector.
Okay.
So then you compute the distance of these vectors in the space.
That's the length of the vectors plus the row.
The length of the vector. So if you want to calculate it, you take the inner product and divide by the length. So
The length of the
Well, but like, so you can never just word in there.
well, the inner product is just the angle, so it doesn't matter how long. So
but the inner product you have to divide by the length of the matrix.
if you take the inner product of the full vectors and then divide by it, I mean, the angle is if you normalize first and then you take the inner product.
Like they're just words by
These are not
word.
unit
So
vectors.
why do they have the current directionality?
So the cosine of V and W is not the inner product of VW divided by the length of V times the length of W.
Yes, okay, yes.
That's what we calculate.
So in this sense, the length of the does not play a role.
I don't know if you divide.
Yes, use a divide.
But that's exactly the meaning of angle.
I know.
That's exactly the meaning of angle.
Yeah, no, I'm not.
But if I don't understand, but all these vectors have the same length, so it shouldn't matter what the end result. Well, no, sorry, no, they don't all have the same length. I don't understand the question. Why would?
I'm just asking if the length has any information in it or not.
Oh, no, I don't think so. No. Only to the degree that it affects the cosine of the angle. Yeah, I see. Yeah. No, it doesn't have any effect. It doesn't matter how long they are.
What decides how long the vectors are actually how big these numbers are, isn't it?
So, for example, this has more weight on this basis than this.
Yes. But just asking, well, this is obviously not used. If you just look at the angle.
But you can actually think about these other different measures of distance. Maybe the length come in some other. Yeah. So this one, for some reason, is the most popular for synonymity. But people actually have done experiments with other measures.
The length heavily depends on the text you study.
that possibly has nothing to do with meaning.
It's a model of meanings based on occurrences in this text. I mean, this is appealing to some higher order insight of what meaning is, which we don't want to do here. I think. By the way, if you can distinguish the grammatical function, obviously you can distinguish nouns from verbs. That should be a small step to also distinguish the two forms of order, which are
You can, yes. So I'm just trying to defend myself because maybe it's not the best example. But if you have a direct transitive verb, you think of it as a relation with three arguments rather than two, the transitive case. So you build a three-dimensional matrix, not a two-dimensional. Okay. So it's a whole different method. So is this clear? Yeah. Okay, so does this theory work? So let's evaluate it on real data. So as you saw, it's very hard to actually talk about synonymity of sentences. It caused a lot of argument. So what is really the right answer? So we have to evaluate this method on real data. So we ran it on the British National Corpus, which has about 600 million sentences. And they claim this sort of is gathered uniformly from all applications, all usages of English, in the news, in science, in day-to-day conversation, etc. So what we did is that we picked 20 verbs from the most occurring verbs in the BNC, and the verbs that were not sort of stop verbs, like not has, not is, and stuff like that, meaningful verbs. For each verb, automatically you can derive two orthogonal meanings, sort of orthogonal meanings, and then look in the BNC, and for each orthogonal pair of orthogonal meanings, come up with sentences that reflects their meaning, and then replace the other meaning in the same context. So pair the sentences, one with the right meaning to the other one with the right meaning, one with the right meaning to the other one with the wrong meaning. Let this method calculate their degree of synonymity. It gives you a number. And then ask human beings to rank these pairs of sentences, for example, a number from 1 to 7. How synonymous human beings think these pairs of sentences are, and then compare the results. Yeah? So here the which ordered Aslan, and the which ordered Turkish delight. The program says these are 0.7 synonymous. Can I have a vote? Who thinks this is below 4? The synonymity between these two sentences. Below 4. 1, 2, 3, 4, 5, 6, 7, 8. How many things is between 4 and 7? Synonymity. 0. There is a lot of difference, yeah. So how do we overcome? So the program says there are 0.7 synonymous, and the human being says there is, so not at all synonymous. But if you guys thought about the similarity of these two, you say it's not synonymous at all. But what would you say about the which ordered Aslan and Lucy was sad? These are the sentences that are far apart. So if you give a number 2 from 7 to this pair, what would you give to these two? You have to go way below. So I think human beings are wrong. Anyway, it's not that bad. Okay, so we did a lot of work, begged a lot of people to annotate these pairs of sentences. So we have 400 sentences. Some of you here maybe did the evaluation. And then there's all kinds of different tests you can run to compare what the computer gave, what our method gave, and what human beings gave. So this is our model. This is very low. We call it the categorical model, which will become clear why. So when the two sentences were judged as high by human beings, and this for example from 4 to 7, the computer on average assigned 0.73, which is very good, yeah? That's very high.
Suppose you compare Lucy was sad and Lucy was happy, which humans would say they're absolutely not synonymous, they mean the exact opposite. What would the computers say?
Yes, we don't know yet about the adjectives, so we work with verbs, not adjectives. There's actually a big problem with adjectives because happy and sad most of the time occur in the same context.
Well, yeah, but how about like Lucy loved and Lucy hated?
Similarly, so they appear in the same
Then we've got
context.
verbs, so that's not a problem you've got. Like, how does the computer deal with that?
So what's your question again?
Well, you said you can't do adjectives, but let's talk about verbs you can do, like Lucy kissed or Lucy hit. Like, how would you do that?
So what do you mean how would
Would they be similar or not? Lucy loved.
Will they be similar?
Lucy hated.
Lucy loved and Lucy hated? I don't know, I have to run the computer to see what it says. My guess is it will be 0.5, so the neutral number. So actually one of the things we came across is that this BNC, although it has 600 million sentences, is not big enough for this kind of test. So you hope that if two adjectives have orthogonal meaning, there will be some properties that distinguish them. For example, you can say a happy wedding and a sad funeral. So there will be enough occurrences of this kind of phrases in the corpus that distinguish the two things. Otherwise, they do occur a lot in the same context.
Yeah, but you would imagine, I think, between like Lucy loved and Lucy hated, they, like you said, different words would appear around them, right? So like Lucy hated blah blah, she was disgusted by blah blah blah, and things like that. That wouldn't appear around, right? When it's the same sort of thing when it said like Lucy loved this and she was so happy when such and such.
Yeah, that's the hope. There's enough examples of that. There's also a lot of overlap with this kind of synonym. So let me get on. So there's other models, so I'm going to describe them and you're going to see how different they are from our method. There's one method which says to compute meaning of a sentence, subject, transitive verb, object, just add their vectors. Subject plus verb plus object. That's very banal, you agree? There's another method which says take their multiplication, just multiply the subject. So if you look at the results for the addition, when human beings said hi, it assigns 90, which is okay, it's a bit too high. But when human beings said low, it also said 90. So it doesn't differentiate between the two at all. And there's the additive method which says 67 when human beings said high, and 0.59 when human beings said low. It's not very good. But anyway, so but specialists in this field say this is not actually a very good measure. So this is good for us to understand, but these two things are not a very good measure. What is very good is what they call Spearman's rho. And this computes degree of correlatedness of two variables. The rank as given by the computer, the degree of synonymity, and the degree of synonymity as given by human beings. So this goes from +1 to -1. So if the rank given by computer increased, monotonously went up, and the rank by human beings monotonously went down, this row should be -1, the correlation between these two variables. So in our setting, it's 0.21. It's very good. The additive is 0.05, so almost non-related. And the multiplicative is 0.73. Which now I would like to say some stuff about evaluation. So when you evaluate this kind of thing, there's a lot of parameters involved. For example, how many bases do you think we have? So I gave 6 there. How many bases do you think a real vector space has built from the BNC? 1 million. And it's very hard to compute with this big number. So we have to reduce the number of bases. But how? What's the good guideline to reduce these things? So we followed the guys who did this addition and multiplication methods, and we took the 5,000 most occurring bases. There are a lot of anomalies. So human beings, so most of the time actually I would say, do not agree and the rank they give. So half of them here say they are very close 7, and the other half say they are not at all close, and they give a rank 1. So we say these sentences that cause such controversial results are anomalies. So throw them away, make a new evaluation list, and get your human annotator evaluated again, and then run the test again. So we didn't do this. They are fine. We didn't do this. The length of the window, so in this case we took 5, matters a lot based on your setting. So we didn't actually change this also. The number of evaluators matters a lot, so it's recommended to have 100. And we have 25 with a lot of begging. So I'm just trying to argue that these numbers can become much better. And then, people actually in computational linguistics argue that these kind of tests are not very good to showcase the compositionality of the method that's used to assign meaning to sentences. Ours is very compositional. We have the meaning of the verb as a relation, acted on the meaning of the subject and object as its argument. And these kind of methods do not showcase compositionality, so we have to come up with a better experiment. So all I'm saying is that we didn't do all of this fine-tuning that other people do, and we already got much better results. At the beginning we were a little shocked, so I thought this was really wrong. And this would be like 100%, and people said 5. So we were a little shocked. Okay.
Seriously?
Yeah, I don't know, I've never done this experiment with statistics or numbers.
I mean, this is natural language, it's highly ambiguous. I mean, if you have people saying from 7 and 1, then...
Yeah. So what is the correct answer, really?
It's not correct. It doesn't resemble that.
What was the tree? What was the tree?
What was the tree, Mehrnoosh? You just erased.
Decoration.
None of us guessed that.
Okay, we can do much more with this setting. So, if we just look at vector spaces in their compact closed structure, so look at the compact closed category that has only one atomic object n, and then you build its tensor product. Etc. So vector spaces form a compact closed category. I think this was discussed a lot. So you take the meaning of your subject and object to live in this vector space n. So I have a subject, C, I, and I. So the bases here are these and I guys. The vector of the object also lives in the same space, C, L, and L. And for the verb, for the transitive verb, lives in its tensor product. So the vector is something like this. The two-dimensional matrix. So if this guy has, for example, R bases, this will have R times R. So I wanted to by thinking of the two-dimensional matrix to be the diagonal of the big four-dimensional one. So this is like a little ugly, so I'm going to write this down as CIJLK. And I keep the CI and the CL. And the basis is going to be a quadruple, and I, and J, and L, and K. So from an I and L, I went to an I and J and L and K. And this is I, J, L, K. Yeah? So I'm going to do something really ugly and say C, I, J, L, K. So I'm going to C, I, J, C, so my C, I, J, L, K is equal to C, I, L, that I have here. If basis n I is the same as basis nj, and nl is the same as nk, and it's 0 otherwise. Yeah, you see what I'm doing? And if I do this, then I can actually open this in a very nice way.
What's this merge state?
No, I'm just encoding the two-dimensional matrix in a big four-dimensional space. We're thinking of it as being the diagonal of the four dimensions. I have some nice pictures.
It's kind of it, right?
See, in fact, I can write it down in a categorical way. This morphism applied to vector of the subject, tensor, vector of the verb, now in 4 dimensions, vector of the object. And you remember these epsilons, if I have one n and another n here, and I put a cup between them, that's an epsilon, and categorically it takes an n, its adjoint, which is in vector spaces of identity, and returns the unit. That's my epsilon. So what I've done is from transitive verb in 2 dimensions, convolution, subject, tensor, object, I'm going to some map applied to the tensor products of the words in the sentence. Now if I claim, I can actually blow this off. This I'm going to call the grammatical structure of the sentence. Let's call it the epithet. And these are the products of all the words in my sentence. So I claim whenever somebody gives you a string of words, W1 to Wn, for simplicity assume it's a sentence, you can build its meaning by applying its grammar, which you can write in this form, to the tensor product of the meanings of the words in there. We have a general theory of meaning. Why? Or how is it that I can think of this guy as the grammar of a sentence? Exactly because of these diagrams, you can give a very good interpretation. So it turns out that these are actually grammatical reductions in a formal way of thinking about grammar called the free group algebra. So if I have this epsilon, so I'm going to put a cup here. I do an identity here for this part, another epsilon here. And this tells me that my verb, 4-dimensional verb, is a linear map, is a relation that takes a subject and an object and produces these 2 lines, which I'm going to call a sentence. That's my sentence. So no matter what grammatical structure the sentence has, I can compositionally build its meaning by this. Yeah? You can then reduce it to the more concrete versions like that and build matrices and compare them. So have used the compact structure of category of vector spaces, it turns out that what I'm doing here, going from 2 dimensions to 4 dimensions, can actually be expressed using the dagger commutative special Frobenius algebras on compact categories. So I've been reading about this a little bit recently. So it seems that every basis gives rise to such a Frobenius algebra. So we've got guys like this, which we call the delta. And what this really is saying is that you give me one vector space, I can copy it, I get 2. And then you have guys like this. I'm not going to call epsilon, call it delta, which tells you have one vector space, so from copying and deleting from nowhere, this copying and deleting from X, you can actually go to nowhere. So that's deleting and that's copying. And these guys satisfy some axioms. So that's the speciality of the isometry axiom.
Two inputs, one side, one.
It's a loop. A loop. A loop.
Yeah. So this one is actually something else. This is called the Frobenius. This is called isometry. There's another one. This. Also the other. Okay. So look, what we're doing is that from something small, we're going to something big. Like exactly, I went from 2 dimensions to 4 dimensions. So now I'm going to be brave and try to give a diagrammatic proof of what I just did here. So this guy, transitive verb, point-wise multiplication, subject, tensor, object. This I can write down. Using the Frobenius algebra structure like this. Yeah. And then apparently, using these axioms, you can prove a lemma saying whenever you have something of this sort, it is actually equal to something of this sort. So that's my lemma. But also remember that convolution is commutative, so I can open this and write it like that to make it topologically easier to follow. Yeah? And then I do this trick here. But before I do that, I'm going to blow up the two-dimensional vector of my verb like this. So I'm going to do this. So this will be like that. It goes in there and this is like that. This is like this. This is like that. And this is the vector of object. And this is like the two objects. And then I'm going to blow the two-dimensional vector, the four-dimensional one, by looking at this bit as my transitive verb, which has now 4 dimensions. So what I get is a transitive verb with 4 dimensions, 2 of them are connected to the subject and object via the epsilon mass, and 2 are sticking out, and this is exactly epsilon tensor identity on n times n, another epsilon, applied to subject tensor verb tensor object. With verb in 4 dimensions. Yeah. You like it? You can do one for adjectives too. No, there's not.
What are these two objects? I mean, you say that's a sentence.
Yeah, so it's the sentence space. So we have to have a sentence space. So we take it here to be n times n. Now there's a subtlety. So it's n times n if you only consider transitive verbs. If you have intransitive verbs, it's n. And if you have ditransitive verbs, it's n3. So now one problem is that how are you going to compare the synonymity of sentences that do not have the same grammatical structure? So then there are ways to embed the smaller one in the bigger one without actually affecting the meaning. So ideally, if you want to really write down the concrete setting in the most general possible way, you have to start with n3. And after you do this calculation, I guess it will be one other diagrammatic move to embed it into the bigger one. Yeah. Yes. I can give the diagrams for the bad which killed the fine line. Do you want that? No.
4 minutes.
4 minutes. I'll do this in 4. So adjectives are also relations, but they take one argument and produce another argument. So if I have, so let's keep it simple. So if I have white, which kills the lion, who kills Aslan. So the meaning of it is I take the 2-dimensional transitive verb, convolution, the 1-dimensional adjective, convolution the subject, and then take the tensor product of this with the object. So I'm first applying the relation whiteness to the beach, and then feeding the beach to the verb. Yeah? So if I want to do the same thing, I have to blow this to 4 and blow this to 2. So the picture starts. Adjective, 1-dimensional, subject, dimensional, the object, with these two connected by convolution, these two also connected by convolution. And then I exactly do the same move as I did before for this form. So this was equal to this, yeah.
So Mehrnoosh, how do you actually represent graphically the bracketing of the thing that one of the Frobenius structures, which is your convolutions, takes the whole thing, including the tensor product? It is not obvious from the picture.
The bracketing, you mean?
Yeah.
So that is obvious from the picture. What is the, I don't know much about this.
So can you remove the bracket around the tensor product to the other side?
Bracket.
Is that associative? At this
Is convolution associative? I guess so, yeah.
The convolution itself.
You can see it from the picture. Just the
that the last convolution there actually consists of two bits, which is the two things on the bottom, two multiplications on the bottom represent the last convolution together. Yeah, they are the last. So they are this one together. So it's not a circle.
First we take the convolution of adjective and subject, and then flip this to the verb.
Yeah, these kind of three pictures cannot be associated, right? If it's associated, it will be flattened out.
So the same. Yeah.
There's some associativity going on between those two. That's
more distributed.
No one would expect distributivity, but it doesn't. Because the tensor has no line.
No, it just means that applied to the vector of adjective, subject, adjective, or
style.
Thank you.
Questions, comments?
Do you have any examples of the anomalies? Do you have examples of the anomalies that people disagree about?
I'm thinking of them from the top of my head, but I have to file them.
Would you agree that the meaning of a phrase in general is no more and no less than how similar that phrase is in some sense to other phrases? That knowing the meaning of a phrase is the same as knowing correlation between different phrases? Quite separate from this particular approach, would you say that's a different way of talking about the meaning of a thing? Instead of knowing the meaning of a thing, it's enough to know how close it is to other things. Or would you not go that far?
So at least for the... Yeah, I don't know, I could think a little bit deeper about how we can think about in the original context, that's indeed the idea. That you know the meaning of a word by knowing the company, the context.
Now suppose I give you a big vector space and I have these mathematical operations and I give you a vector and I say, what does this mean? You can't tell me what it means, you can only tell me mathematical things about it. You need a way to root your mathematics in the real world and in the concepts that we talk about with our language that we understand.
It's all very important. And we run the evaluations, not somewhere I don't understand, not very getting to.
I think I'm asking a question more about how this can fit into some more general idea of what a language is and what it means for something to have a meaning, whether this can ever be fully powerful in getting to
something that's a wiser word.
Well, I mean, maybe to interpret what you might be getting at, this might relate to the thing you start right off at the beginning with. It's sort of, how does one relate this kind of approach, which is about correlations, in a sense, with the sort of the old idea of meaning by denotation, which you referred to right at the beginning of the talk, the old idea of logic things. So you think of, the words denote things in the world, and relationships between those things. So I mean, is there a way of relating this view of meaning to that tradition view, which, as we know, has its problems, but nevertheless also seems to get at some reasonable intuition?
We have, yes. can do the same maneuvers and get a vector here, then you can say a sentence is true or false, like in the logical. Now it's not as clear what to do with logical connectives, like not, and, or, and things like that. In the big setting. Here it's clear. So not is just so up. But it's not clear how it is in the big setting. Yeah, does that answer your question?
To put it another way, suppose you imagine a transformation of the language where you interchange the words which and lion, which and as that, and you interchange the words terrible and good. And you can imagine some grand automatism of the whole system that maintains the correlation coefficients, but completely changes the meaning as far as the humans are concerned, because we have our own ideas of what kind of terrible or happy or sad based on animal reactions to things. And if you change the words, that would destroy the link to our more basic feelings and instincts. So I think this is what Jamie was asking, is how might, is it enough just to have the correlations, or do you still need some kind of thing to what can be expressed more basically?
Actually, maybe I should say this. So, this vector space idea I presented as co-occurrence or closeness to other words, but you can actually play a lot of different games with it. So if you, I guess that's related to what you said. So if you look at the end of dictionaries, you see that each word is being described by a set of other words, not based on in the context in which they appear, but based on what you were saying. That, for example, the emotion liking is based on more primitive things like loving and hating, which really come from the hormones. Then you mix them in a magical way and you get liking. So then you can actually, don't look at your corpus at all, get these things, because what you're describing it has to be documented somewhere. So let's take the back of the dictionary and take the basis to be these smaller words and then define complicated concepts based on the hierarchy given to you by the dictionary. So then you can create sentences based on the concepts and not based on the concepts.
But Mehrnoosh, suppose you didn't know any Russian at all and somebody gave you a Russian dictionary in Russian, telling you what Russian words mean in terms of other Russian words. This would be no good to you for learning Russian. They're effectively giving you these correlations, right?
Yeah, you have to
but
have
you
some
can't.
initial, yeah.
You have.
Yeah.
So I don't
That's
think.
why this witch and wardrobe was a good example. You know some words like winter and spring, but you don't know Narnia and Aslan.
So how can an approach like this be enough by itself? How can an approach like this be enough by itself? How is it anchored into a language that a particular language that humans would already understand?
I think that's a very
by
question. What do you mean, the language that you use?
I question whether or not just feeding it a Russian dictionary, though, is completely useless, right? Because you still get correlations out of something like that.
Well, I think that's what they're saying, you get the correlation.
It's being described by a set of other Russian words, and if I don't know any Russian, this is not going to help me.
Right, but still, if you just feed the dictionary into this method and then use it to analyze something else, it might still tell you
You
something
say that, but what about a blind person? A blind person can learn.
Studying correlation in Russian and comparing.
Blind, paralyzed person can learn to speak. These people have no input other than what they hear. I think it's a
topology of correlation might
profound
actually doesn't tell you something about a word. Maybe not.
I think this might go to a lot of compositional meaning approaches, but this seems to say that the meaning of a thing comes primarily from the meaning of the words, that the meaning of the sentence is arrived at from the meaning of the words. And I mean, I think there is in semantics like a recognition that the actual structure of a sentence has an inherent meaning. Like an example, I think I mentioned previously, is like Jeff drove the car across the road has a meaning of direction, that you can say like Mehrnoosh sneezed the mug across the microwave, and it still has like, that shouldn't make sense, but we always understand a certain agent and directionality, and that's inherent in the structure, not in the words.
Yeah.
So could your approach?
Yes, actually we absolutely do that. So we say the meaning of a sentence is the meaning of its words, the grammar. But not only the meaning of the word, not only the grammar, like the logical approach, but an interaction between the two. The grammar acts on the meaning of the word.
But didn't those ends, didn't that come from just like numeric relations between the words themselves? Like
the ends in this case come from, yes, from co-occurrence, if you want. But then we put the grammar on top of it. You can actually, so we've also done the following. Not take n to be just a plain vector space, but take an n whose bases are words annotated with their grammatical roles. So instead of just saying horrible as an adjective, you actually say argument of horrible. So you do not count how many times the word you are interested in, like the which, has co-occurred with horrible, but actually how many times it has been directly modified by horrible, like horrible food. Not that the which ordered the horrible food, but that one also counts. Yeah. So you can play with these things a lot, but I guess this is the major point where the grammar comes into the picture.
Yeah.
So Bob had this notion of connectedness. Now your TV2 connects two of these tangled things, yeah? Have you investigated if you find verbs which disconnect? Like
Yeah, I didn't understand what he said yesterday.
so if you
It's very hard to get information out of Bob. You know how arm wrestling, it's so hard. If anybody in the quantum group wants to help me with this thing, get me out of the grip of Bob. I didn't understand. That's why I was asking the question yesterday about connectedness.
No, but
I didn't understand.
and for example would disconnect something.
But where is it? So
if you
these
have
are all
I'm sad
disconnected.
and the sky is blue, that would just split into two things.
But these are all disconnected, right? Because this tensor
No, the TV2, if the box could be separated.
The
So
TV2 is connected.
I think for verbs it would be hard to find one which is disconnected.
I don't understand.
But for other words,
Can you explain?
so suppose you have one of these rules with two lines in out, whatever its grammatical meaning is. Yeah?
So I have something like this.
Do you find words so that you can replace this by two rules with two lines? Yeah?
Oh, so you want to replace the word
Yep.
like this to this.
Like in the sentence, I'm sad and the sky is blue, the end connects two sentences, but actually I could just put a full stop in between.
There would be.
So what's the verb?
Well, it's not a verb, but I'm
You're
very
talking about the
linguistic.
meaning of conjunctives, like Maybe that's what makes them different.
The dog runs and the grass is green.
Yeah.
So why do we put and there in Barcelona?
I don't know. Well, you could do that. You could say that.
But there is a correlation.
But they are totally unrelated.
But you haven't investigated if such a correlation could be broken. So your tensor, that means that your tensor which you get for your correlation is actually separated, yeah? So it's a rank 1 tensor, or at least say a low rank
that for
tensor.
the verb it shouldn't be the case, because then it means...
I guess we have to close because we have to move on. So we thank Mehrnoosh again. 10 minutes.